Okay, so the last little bit that we're going to do today is going to be systems in which we've got carbonyls that are separated by 3 carbons, or carbonyls that are separated by 5 carbons. That's going to come in a second. So the classic example would be what we call the Claisen condensation. Maybe I should just use a different screen here. Claisen. Yeah, let's see if this is that what I want to do? Is this what I want to do? Right. And I'll just call this R. This is okay. So yeah, let's pretend that this is what we want to make. There is, if we follow the enolate methodology, we would start with these 2 components, and I guess I should, if we wanted to idealize these, we would have, this is one component, and sorry. This is the other component. And so for the electrophile, what we need, which is important, is a leaving group. Now, the interesting thing about the Claisen condensation is you can, in certain instances, you can mix, you can have 2, okay, so let's pretend that our specific 2 components are the cyclopentanone plus this ester here. If we were to throw in a base, for example, there's actually there's 2 protons here, which would be the same as the 2 over here, these guys. So they're equivalent. But there's 3 alpha protons here, which could also be technically deprotonated. So it turns out that when it comes to the pKa's of alpha protons, there's certain things that are important. One, so if you're going from ketones to esters to amides, the pKa is, going in this direction, is increasing. So you can deprotonate a ketone easier than an ester, which can deprotonate easier than an amide. They're all in the low to mid 20s. So I think a ketone somewhere around 21, 22, something like this. So you would typically, and there's another thing to bring up too, actually. So if you had methoxide in here, what's going to end up happening is that there's going to be an equilibrium which is formed where you generate a tiny amount of this plus methanol. And what can happen is that this enolate can then attack the ester. So let's do that. Bingo. Bango. Goes up, goes down, that leaves. And then you would generate your final product, which would look like this. And the interesting thing about this is that you have in it this proton here. So for everybody who has taken the lab already, this is like we're using a malonate to do an alkylation reaction. But this little proton in here is super acidic. And so it'd get deprotonated immediately. And you would have a stabilized enolate here. And if there wasn't a particularly great electrophile around, it would stay like this until you worked it up with H+, and you would get your final product. Now, the way I've drawn this, there's one critical thing, which is sort of one problematic thing, which we haven't discussed yet. And that is, so if you add a base, the most acidic protons are these guys. No problem there. But the second step, which I've drawn in orange, in fact, the most reactive electrophile is this guy. So you have to worry about, because esters, the lone pairs in an ester, they're donating into the carbonyl, which makes that carbonyl less electrophilic. So doing it with just straight methanol or methoxide and setting up an equilibrium, because this would be an equilibrium like between these two, and the favored side would be the ketone, not the enol. Probably the main side product would be the aldol reaction, so the enolate actually attacking the starting material. So to do something like this, you want to have, you don't want to rely on an equilibrium unless the electrophile is more reactive than potential other starting material. So there's two ways to do this. One is what you've seen before, is to use like LDA, and then you generate your enolate, and then you react it with, you quench it with an ester. Or you can try to get away with using an acid chloride. But there is the potential side reaction when you're using acid chloride of it alkylating at the, or doing the reaction at the oxygen. So you could do this, and then you could add your electrophile, which would be the ester, and get your product. You can set up some clays and condensations in which you can use methoxide, and I'm just trying to think of a good example of that. Unfortunately, they're all escaping my mind right today. It's definitely a Monday today. So yeah, that's if you generate this and there's no starting material left, i.e. ketone, then there's only one pathway for the reaction to follow. So that's one of the nice advantages of doing it that way. Let me see. Right, this is synthesis. So this is very similar to what we are doing in the lab. In fact, this first reaction here is exactly what we're doing in the lab. So we're starting with, oh, come on. We are starting with diethylmalonate. We're using sodium ethoxide and a good electrophile to make this compound. Later on, we're going to do something neat with it. Here in this synthesis, which started up there, they're doing an aldol reaction in the second step. So you start with an aldehyde, and that, so you deprotonate it here. This comes in attacks, the electrons move up, and it gets protonated with acid at the end. This last step we'll do on the next sheet. This is what we call a decarboxylation reaction. So we are removing, and this should actually be an H, not an ester. This is removing one of the carboxylic acids. So yeah, there's quite a bit of stuff happening here. So in this retrosynthesis, we've got 1, 2, 3, 3 carbons coming between the carbonyl and the hydroxyl group. So possible reagents would be, okay, well, let's use this, the anion here and our aldehyde. That works. And then there's another disconnection here for this allyl group. So you can actually start with the malonate, add the allyl bromide, and then this part is going to be removed through the functional group interconversion in the end before we actually, yeah, it's going to be removed. It's going to be decarboxylated. So basically, okay, yeah, so this is, okay, that's a good point. Let's reshare this, share the next. Okay. So this is a really, really useful, essentially this, okay, negative charge, we're going to deprotonate that. This is essentially a really good equivalent to just an ester with a negative charge. So esters, the pKa's of esters are higher, so you need to use stronger bases to deprotonate them. Whereas with a malonate, because this negative charge is stabilized by resonance between the 2 carbonyls, the pKa is lower, and you can use weaker bases, even as we're going to do in the lab using OR minus. So that gives it certain advantages. The second advantage is because it's a stabilized anion, there can be quite often the alkylation reaction has fewer side reactions. So for example, let's pretend that we've got, say, something like this. Oops, it got an extra electron. And we're trying to do a substitution reaction. So we would expect this to come here, and that to leave, and then we would have our final product. One, two, three, four. 1, 2, 3, 4. Okay. all good. Sometimes with enolates, if a potential side reaction is that they could conceivably do E2 elimination. So you just, so this would grab a proton and then you would eliminate the leaving group. It's a, so that's sometimes a side reaction. The other thing is that generating enolates of like esters and amides and these sort of stuff, because they require stronger bases, you need to do these at lower temperatures to, because remember, lithium enolates they're stable at -78, but if you warm them up too much, they decompose. So as opposed to the malonate, which because it's stabilized, you can run these reactions at 0 degrees or even room temperature, which is what we're doing. I think, in fact, I think even some reactions, they actually heat them up. So there's stability issues, which makes these things, the malonates here, more useful, easier to work with, and all that sort of stuff. The only thing you need to worry about is actually just, if you want this, all you need to do is find a way to get rid of the other ester, and there is a way to do it. And we'll basically explain that. So once you've made what you want to make, so let's pretend that we put our allyl group here. And what we're looking for is this. I'll even put OR here. There's a way of decarboxylating these reactions. So remember, if you have an ester and you react it with a base in water, so an aqueous, this reaction is basically called a saponification. So it's a hydrolysis where we're converting the ester into a carboxylic acid. And so when you use like sodium hydroxide, both sides of this are going to be, okay, so let's do this. OH minus. This comes in here, electrons move up, electrons move down, you eject OR. Your product is going to look like this. And this is quickly, the proton there is quickly going to get removed, because having a carboxylic acid in the basic solution, it's going to quickly get removed. But the same thing can take place at both carbons. So you're going to have a dual saponification reaction. So your product here is going to look like this. And I'm going to protonate it after the workup. So it'll be the dianion. And then when you add your acid at the end, it's going to be the diacid. Something like this. Then if you heat this guy up, something really interesting happens. And in fact, I think you can heat. Actually, doing the acidification step isn't always necessary. So you can but the mechanism looks prettier when you do it this way. So that's how we'll do it. The principle is actually the same with regard to so we are going to lose CO2 gas. So heating this up is going to, we're going to lose CO2 gas. And the mechanism for this is, as I said, fun. Okay, so we are going to grab this protons. These electrons are going to go here. These electrons are going to go here. I'm drawing it as that the pi electrons are doing that. They're probably not, probably lone pairs, but that's okay. And so what we have is this. So the CO2 gas bubbles away, and we have effectively an enol. And then this will just tautomerize to the acid. And so with the carboxylic acid, this functional group can be converted into a whole bunch of different things. So it's a way you could make, you could reform your ester, you could convert it into an acid chloride, and then the acid chloride can be converted into basically all of the carbonyl functional groups. And so it's a relatively neat reaction to do. Now, you're heating it up and you're producing gas. So that can be, when you're doing it on a large scale, you want to be darn careful about it. But it's a neat little reaction as to what's going on. So these malanates are really, 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 really useful. They're really, really useful nucleophiles because they've got a reactive alpha like carbon. And the carbonyls themselves with the esters, one of them can be decarboxylated. They can be converted into alcohols through reduction or reactions with Grignards. So esters can be converted into a whole number of different things. You can, as I said before, you can convert them into carboxylic acids, which can be converted into. So there's lots of functional group interconversions associated with the esters themselves. So yeah, so the malinate, it's a really fascinating little functional group. So on the slides, oops, on the slides here, we had new share. Sorry, I'm just having a mental block here. So on the share, on this here, I said try to make this compound. And it's interesting because if we look, 1, 2, 3, these carbons 1 and carbons 3 are part of the malanates. The only thing which has happened is they've been reduced and converted into an acetal. So it's a functional group interconversion there. So this would be one of the this would be one of the starting materials from the very, 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 very start. You'll notice that there are 2 groups so this bond needs to be made at some stage, and either the phenyl or the amine bond needs to be made at some stage, based upon how we would disconnect that. Well, the rest of the stuff which happens with the acetal, it's just a functional group interconversion. So if you've got, say, R1, R2, this could be a functional group interconversion. You could have reduce these to alcohols, and then further functional group interconversion, basically make the cap it off with the thing. But these other steps here, you can, there's some neat stuff to do with this. Shall we try to break this apart? I think we should. Okay, so let's redraw this. Okay, I've redrawn this here. Okay, and I'm going to highlight this part here. So this all comes from our malonate. If we had them like, and I'll exclude the rest of the molecule here, but the two things we could do if we wanted to make it this 6-membered ring, the first one would be a reduction with a strong reducing agent like lithium aluminum hydride. This would make this. And then the last step would be if we made an acetal. So we would use, I guess, formaldehyde plus H+, and that's going to make the acetal. So that's how the functional group interconversions would work with this molecule. But these would happen at, this would have to happen at the very end. If we went back to our, in fact, anyway, I just thought of something. If we went back to our principles of how, like if you're deciding on breaking, doing a retrosynthesis and all that sort of stuff, which of these bonds would be the one that you think would be the last one that you would want to include? Like, which would be the final disconnection without the, like, the functional group interconversion stuff, which we're going to do at the end anyway, but right prior to that, what would be the thing that would, which bond should be the one which is broken?
Green one?
The green one. Okay, why the green one?
Because the most reactive, so you want to do it last.
Right. Okay, good. So, excellent. Okay, so then if we're going to break the green bond, now let's put back our structure here. So is our nitrogen going to be the nucleophile or the electrophile?
The nucleophile.
Right. So this is going to be N-, and we want this carbon here to be plus. Good. Okay, now next question is, so our nucleophile can be, all we need to do is our actual reagent can be H and Me2. So this is our actual reagent. So that's relatively straightforward. What are we going to use for the for this for the electrophile. What would be the best reagent for this? What are some what are some possibilities that we could use?
Could you do a substitution reaction?
So like an SN2 type thing?
Yeah, because it's only secondary.
Okay, so
I guess it would actually be tertiary if you had the.
OR. So we would need a bromine here, something like that. Okay, now the good news is there is a way to put a bromine in this position. And that is with, we did it in organic 2 today, actually. NBS UV light, because it brominates selectively on the benzoic carbon, right? So okay. And then if this was the route we were going, which I guess we've got to offer up some bonds to break. This one in orange or this one in purple. Which would be the better disconnection there?
Purple.
Okay, purple. Good. Purple. Okay, so there we would basically have our malonate. So this would be the nucleophile, OR, negative, and benzyl plus. So our reagent could be benzyl bromide. And our malonate would just be the diethyl malonate, for example. Okay, so this synthesis is entirely possible. My only concern is this step right here, the NBS and UV light. There is a way to reduce the number of steps for this synthesis by using what would be a like a 2-group disconnection type of stuff. And it relies on the fact that one of the, let me go back to the, and I don't expect everyone to remember this because it's just, it relies on the fact that there is a possible, when you're doing an aldol reaction, which we talked about last class, you come up with a situation where you got carbon 1, 2, 3, that 3-carbon system. But if you leave this going for too long, you can lose water, and you can form a double bond beside the carbonyl. So if we look, and remember, what was the interesting thing about enones with regard to one of the things that was interesting about enones is that this carbon here is electrophilic, right? So if we have, let's do a new share. We're let's do some resonance structures. Ooh, positive charge beside a double bond. Oh, that's another possible resonance structure. And there we go, right? So this carbon here is electrophilic. So nucleophile can attack. So if we go back and we look at this initial disconnection that was made here, you will see that alpha carbon, beta carbon, alpha carbon, beta carbon. If we had a double bond between those two components, our starting material could be this. And we can do our, we can have our little our dimethylamine, and it can do a Michael addition and generate our, so this green bond, they can make that bond there. So, and then the next bit is how do we do this? And the answer to that is the aldol reaction. So we would have our two components being the malonate, which will be the negative, and benzaldehyde. We just let that reaction, we just let it go, and it becomes, dehydrates over time. I guess we should probably do the mechanism of that. There's also, I believe that doing this reaction with the aldol, there's another name for it, the Nova-Nagel condensation. And there's a couple of I'll have to, as I said, it feels like a Monday because everything isn't, my brain isn't entirely working very well. But I'm not even going to try to write out Nova-Nagel because I'm going to spell it wrong. But I'll bring that up on Tuesday, unless you want to look it up. But yeah, so this little system here can be made from the diethylmalonate, an aldol type reaction where the product gets dehydrated, followed by a Michael addition using the amine, and then it's just transforming the malonate, reducing it, and then converting it into an acetal. All sorts of fun stuff going on there. But that was the that's one potential way of doing this whole system. Anyway. There's probably a million questions. But let's just do one little thing quickly. The elimination. So let's pretend that you had acetophenone and benzaldehyde. And you did an aldol condensation using, this will be under thermodynamic control. So you're using just a little bit of, say, sodium methoxide here. So as I said before, these two are going to be in equilibrium, which is going to strongly favor the ketone. But you're going to generate a little bit of enolate. So this enolate is then going to look for an electrophile to attack. And if you're comparing a ketone to an aldehyde, the aldehyde's more electrophilic because that methyl group's pushing electron density, which means that this has got a larger delta plus. So we'll attack, electrons go up. And you have a product that looks like this. Negative. And if this reaction is being carried out as like sodium methoxide and methanol, eventually this is going to get protonated by methanol, and you are going to have, stop that. A system like this. So this would be your aldol product. Now, unfortunately, if you just keep it stirring, eventually some methoxide is going to say to itself, well, look, we've got some alpha protons here, so let's deprotonate that to generate the enolate. And then this does something really interesting. These electrons come back, these electrons go here, and that boots out that. And we end up with our hydroxide is the leaving group. And you might say, well, wait a second, we were told that an organic 2 or organic 1 actually can't have hydroxide as a leaving group. It's a terrible leaving group. Certainly you can't have it for an SN1 or SN2 or E1 or an E2 elimination. That's true. This mechanism is interesting. It's called the E1CB. So it's an E1 elimination, and the CB stands for conjugate base. So the key point here is that you need to have some acidic protons, and we're not just removing that proton and eliminating the hydroxide. It's being stabilized in the enolate. And then from there, entropy sort of takes over, and you boot out and you generate a conjugated system, which is thermodynamically very stable. So there's a couple of things going on with that. But this is how aldol reactions can be, if you leave them if you don't pay close attention to them, you can always lose that OH group, and you generate a conjugated system where you've got alpha and beta carbon. There's a double bond between the alpha beta unsaturated carbonyl, I guess is the best way to describe that. So that's a neat little reaction. Okay, now what was I going to do? Okay, so basically class is over. So today at some stage on Moodle, what I'll do is I'll put up like your assignment to submit the assignment. I'll put a little thing there where you can just upload your reducing agent to that. And then later on, what I'll do is I'll send everyone an email about this. I'll post, because what everyone's job is going to be is to look at everyone else's assignment and evaluate the little factoid sheets, right? So I'll give you some electronic versions of the factoid sheet, and you're basically going to be assessing everybody's assignment, similar to the way you assessed mine. So I think everyone did a pretty good job. In certain places, particularly if you're going to deduct marks for something, it's good to explain why. Saying like 0 out of 3 without any real good explanation isn't particularly, that's not, that's, but everyone had some explanations, but some of them could have been a little bit more detailed. That's the other thing. And the other thing, which a couple people gave me really good marks, like 5 out of 5, when I left little bits of things out. So just keep that in mind. My little reduction was certainly missing certain things, so that people caught up on, certainly caught up on. So, but the high mark I got was 14. Yay. And the low mark was 10. Sad.
I wonder who that was.
What's that?
Well, I wonder who gave such a low mark.
Two people did. So obviously they both of them had good cause. It wasn't, they weren't alone. I think my average was around, I should calculate it. I think there was an 11 in there, maybe 2 11s and a couple 12s.
Dr. Hill, what would you give that?
What have I given it? Well,
Yeah.
the more I looked at it, the more I realized, oh, I'm missing this and I'm missing that. Probably, was it an interesting example? Yeah, I think it was. Were the references good? Yeah, I think they were probably pretty good. The presentation I thought was not bad, but the mechanism was certainly missing a couple of, like particularly with regard to the regiochemistry stuff, it was missing a whole bunch of information there. Very little explanation for that. The first part of it was okay. The advantages and disadvantages probably could have used a bit of help there. People picked up on stuff which was, what does this mean? And that's not very clear. And so those would be the two places where I thought it could have gotten, I could have gotten hammered on, and I was. So so it was nice. So like what's the best the way, as long as like there isn't a number which is correct, right? So if say you've got assignment A, B, and C, and you're evaluating all of them, the key part is to be consistent. So if you're a hard marker, as long as you're a hard marker consistently across it, it's going to be, so let's say that person 1, 2, and 3, so person 1 gave, these are all 15, person 1 gave 3, 12, and 11. And person 2 gave, I don't know, 13, 12, and 12. And person 3 gave sort of 11, 10, and 10. Or 12, 10, and 10, let's say that. And someone else gave 13, 10, and 13. There's a sort of a, there's, what am I trying to say here? There's sort of a trend for certain things. Like, it's just as long as things aren't wildly, stop it, cat. Oh my God. You know, my cats can open up doors. We got those sort of lever doors, and one of them can stretch up and pull it down, and it's nuts. Anyway, so she broke him. As long as it's consistent, the actual number isn't really important. It's just the way that it's consistently done. That's all. And it's fun because I won't pick up on certain things and other people will. It's like, oh, that's good. I missed that. And so whenever that happens, that's like enlightening. And
peer reviews for.
That's right. Yes. So it's kind of like that. So which number was right? I don't know what number is right. As long as people are consistent with the way that they do it, then it's good.
So wait, how's our final mark? Like, is it just gonna be an average of what everyone else gave us?
Well, I'll show you how it works. Because part of the mark is based upon, I'm going to do an evaluation myself. So there's going to be me. And then the way that each assignment works is that part of your mark will be what everyone else thinks, a certain percent of it. Part of it is going to be what I think of it. And then part of it is going to be my assessment of your assessments.
So your grade for your grading.
Right. So there isn't a, I don't think there's a way, in case people were like, and so it's not necessarily the whole number isn't going to affect how it works, right?
And there's no, like, we'll know which assignment we're grading. You're not trying to hide, like, Roman did this one, so I'm marking Romans right now.
Oh, what I'll do is, yeah, you're actually, the way that this, did I do that before? I think I just put I think it was just the reagent. So
Okay.
if people don't really know what reagent people are doing, then you won't know.
Well, I put my like identifying info at the top of mine, but
Oh, what I can do is I can erase that.
yeah.
Okay,
So-
so don't put your names on your assignment.
I mean, he's gonna want to know who's though.
But he knows who has what reagent.
I guess so. Yeah.
Yeah. So just see, it's weird because this like usually in this class there's 3 people or 4 people in the class, so it's like everyone always knew who had what, right? So this class is a bit bigger, so it could be a bit more anonymous, so to speak. What I'll do is I'll make sure that the identifying thing isn't there. Does that make sense?
Yeah.
Yeah.
So yeah, I'll set up the Moodle thing so you can upload your thing to it, and then from there, I will distribute out all of the like the assessment form and all of the assignments. I'll probably post them all in a file on Moodle too, so you just go and look at them. Oh, this is exciting. It's always fun. And then the neat thing is that everyone's going to learn a bunch of fun chemistry that you will have taught yourselves.
And we're only assessing one other, or how many are we doing?
All of them, except for yours.
Oh, okay.
So yeah, you guys, you're going to have a bit more work than the last class, which had 4 people in it.
Marking practice for all those courses you're gonna TA.
Right, exactly.
Wait, so do we do our own?
No,
No.
you don't.
Okay.
I mean,
Yeah.
like when you're making it, you kind of should.
No, I didn't know what he wanted.
Yeah, you're not going to be doing your own assessment. No.
100%. I'm amazing. Gold star.
Yeah. Okay. Excellent. So yeah, I think that's it.
I had a
So,
couple of
Do you have
I
any
had a
questions?
couple of related to my reducing agent stuff, but
Okay, well, do you want to hang on the line afterwards?
yeah, not a problem. I just didn't want you to hang up on me before I got a chance to mention it.
Okay.
That's the same too, Dr. Hill. Just quick one.
Okay. Well, if everyone else who doesn't have a question wants to go, you can take off and then, okay, so we'll, is it a private question or is it
No,
something?
it just pertaining to my assignment and like I probably spent like 4 or 5 hours last night poring over research papers and I couldn't wow. My thing's already 4 pages long.
Oh, wow.
Yours was 2,
Right.
right? So I'm basing mine off of your initial template, but I'm also you gave me dip chloride because I asked you to assign me one.
Right.
It is really cool. I found some good like I've basically taken pictures from all these papers, and I got the mechanism, but there's like, it does a lot of stuff.
Yeah,
and
I
I'm
would.
trying to focus on just the reductions,
Right.
because it also does some like aldol linkages, right?
Yep.
Which is a reduction, I guess. But I'm just trying to figure out, am I going overboard, or like,
Yeah,
how much do I need to have on this thing?
I
'Cause I'm
would
not-
just highlight one of the reactions that it does, which you find to be the most interesting.
Oh crap. And I was having a hard time finding out information about the regioselectivity of it. Like,
Oh, so the regioselectivity part on my thing was specific to the birch reduction. So if you've got like dip chloride, you might be able to. It might do something fun like.
well, the biggest thing I noticed was that it's mainly affected by steric hindrance.
Right.
Like, it'll choose one side or the other based on how big the groups are, right?
Right. So you could highlight that interesting feature of it and just within the mechanism of it.
Okay. Because like,
And it doesn't
from-
need to be called
Sorry.
like regiochemistry. It could just be called like stereochemistry.
okay, just from what I was looking at, there are effects if you stick things on the ring, but a lot of the diagrams were like X and Z, and then it had like a list of things for them, and I was like, I don't really know what's what there. But it is cool that it essentially gives 100% one racemate.
Yeah.
Is that right? Yeah.
Yeah.
So I've kind of overdone it, is what you're telling me. I had like, let's see, what do I got here? I had it like broken down like it does reductions on, where the hell did I stick that? I might have deleted it actually. Oh yeah, no. Reductions on alpha keto esters, reductions on gamma keto esters, stuff like that.
Yeah, that's it, it's so people have done lots of studies on all those things then.
Mm. Well, it's the organoborates.
Yeah, exactly.
Like, you can stick whatever functional group on there. It's just that chlorine seems to be the cheapest / most effective to make, I think.
Yeah.
And like, I noticed you didn't put it in there, but I put a section at the beginning on how it's like made in the lab, like how the reagent's synthesized.